Okay, second presentation is, let's say, completely different than the first one. We are talking about row migration and row chaining internals. Of course, I will skip this one because it's still me, still the same book and so on. Now, why I'm talking about row migration and row chaining, I would say mainly because it's not, in general, it's not very well, a topic which is not very well understood. And in my opinion, the problem is also that Oracle never described it correctly. Okay, now in the last couple of releases they try to fix some stuff, but the problem is that sometimes in the documentation, but also in the software, they say chaining and in fact it's migration. Sometimes they say migration is chaining, or yeah, they confuse a bit the two topics. Okay, and at the end I think that a lot of people got confused by these two things, which are quite different, even though some of the problems they cause are similar. Okay, so I would say it's nice to try to make some an introduction how is row chaining, row migration, and then explain in detail what they really are. To explain what row chaining and row migration are, let's start from an Oracle block, from the data block. And be careful, data block it's also used, for example, for indexes. But what I will describe now is really a data block, for example, for a regular IPT table. Basically, you have a block, you have always a common block header at the beginning, you have a common block tail at the end. There are just two parts of information which are in all Oracle database blocks. It doesn't matter if you are speaking from control file, airman backups, redo logs, you always have some parts which are there. For example, in the common block header at the beginning, you have the type of the block that tells you whether the block is a data block, it's an undo block, it's a header, file header block, whatever. Then in the case of a data block, you have the transaction ender and the ETL, interested transaction list. Then you have the data header and table directory to describe what is stored into the block. Notice that table directory is only important in case you have clusters or compression, because in case of clusters and compression, you might have several tables inside a single block. And so in the table directory, you find a list of tables which are stored in the block itself. Then you have the row directory, which is which contain basically it's a piece of, let's say, of the block which has a reference inside the data header, or better in the table directory, because the table directory tells you, okay, at this offset I have my rows. And inside the row directory, basically you have for each row which is stored in the block, you have one pointer, and the pointer shows you where the data is stored. For example, I have one row which is stored there, a second one here. Notice that even though you delete a row, it might stay in the block, it's not immediately deleted, so they just set a flag inside the row and the row stays inside the block. And if I store more rows, you see that in this case I have 8 rows. You have with these 8 pointers, you know where the data are. By the way, it is interesting to also to point out that the position inside the row directory is what is referenced by the row ID of a row. At the row ID, if you take a restricted row ID, you have the file number, block number, and row number. And the row number is the offset inside the row directory. Is not the position of the row. The row, so you will see later on, can change of position inside the block. Okay, so it's just the logical row number. Okay, and the point is that inside the row directory you have the offset inside the block where the row is actually stored, and that offset can change. So this is basically a regular database block. One pointer that was missing here is this one. When you have a transaction which is modifying a row, it means that it locks the row, basically what you have is a pointer that goes from the row to the interested transaction list. And in the interested transaction list, you have information like the transaction ID and stuff like that, where to find the undo and so on. Okay. Now, if we look now at one row is composed from an header at the beginning, a few bytes to describe, for example, how many columns has the row, if the row is locked, if the row is deleted, stuff like that. And then you have for every column, you have two pieces of information. One is how much data is stored in the column. So it's the L, the length of the column, and the data itself. So you might have here, I have 5 bytes to store a number, I have 10 bytes to store a string, I have 3 bytes to store a string, and so on. Okay, and the number of columns which are available in the row is stored inside the header. Okay. If you look a bit closer at the header, now we are in this part here, the header. Basically, you have 3 bytes which are always there. If we are talking about non-clustered table, clustered table are a bit different. But in case of a non-clustered table, you always have 1 byte of flex. This is where there are stored information like I'm deleted, I'm migrated, for example. Okay. The lock is the pointer that we have seen before to the ETL. We go back. It's this pointer here. Since we are inside one block, 1 byte is enough to reference any position inside the block. And then here, 1 byte to specify the number of columns of the row. There is an important limitation. Since we have 1 byte, we can store in one row at most 255 columns. Okay, and we will see this limitation, why it is important later on. Okay, and it's an important limitation because we can store in an Oracle database 1,000 rows, columns per row, but in the physical level you can store only 255. Then there are SCN information which are optional. They are only stored if you specify row dependencies at the table level. And then what is important for this talk is the row ID next piece. That means if the row is chained or migrated, then you have some flex which are set here, and then here you find the row ID where to find more information. We'll see some examples in a couple of minutes. In any case, this is where all the information about chaining and migration is stored. Inside the row, there is no information somewhere else, segment level or extent level, whatever. Okay. Now let's start by talking from row migration. Row migration happens when you basically update a row and the new row is bigger and it doesn't fit in the block where it is stored. So what you usually have, for example here, row 4 also use this part of the block. After the update it needs so much space, since there is not enough space to store it inside the block. What they do, they split the row in two, and they call this part piece. Okay, so this is the piece 1 and piece 2. And so part of the information is stored here and part of the information is stored here. Or better, in the case of row migration, you have all data which are stored here. And in the row piece number 1, what you get is only this information here. So you only have the header. It tells you I'm migrated, okay, if I'm locked or not, depends. I have 0 columns, and you find the information there. Okay. Why they keep this information? Simply because one of the principles in Oracle is that they never try to change a row ID. Okay, so if you have inserted one row and this row has a specific row ID, they try to never change it. Actually, if you are not using Exadata with HCC compression, they never modify the row ID except when you specify, for example, on a partition table that row movement is activated, or in case you do a shrink, alter table shrink space or stuff like that. Otherwise, they always try to keep the row ID fixed. Because if they change the row ID, of course, they should change all the indexes and references it. If you have an application that uses the row ID, it would also be a problem. So they try to not change it. So they keep this piece even though the piece doesn't contain any piece of real data. So everything is stored here. So this is a migrated row. Just an example. Let's take a free block. We have the header, the tail, which are always there, and then let's say that we have the PSD3, which is set to something like 10% here. If we start inserting data, basically what Oracle does starts inserting the data in the block, and interesting, it inserts the data at the end of the block. Why not at the beginning? Simply put, because if you start inserting data, the row directory that we have here has to grow. Okay, and so if they would start from the top, they had to move the data every time. So they start the header, let's say, grow from the top, and the data, they grow from the bottom. At some time they will hit the same point. So if you insert few rows, we just insert data. Okay, here I have an update. I want to update this statement, this row. Now, if the update makes the row bigger, as we have seen before, the row can be moved inside the block. So what they usually do, it's not moving the other rows if it's not needed. They just delete the row from here and put it somewhere else inside the block. Okay, and of course changing the offsetting the row directory. We insert number 7. Now we have to insert one row. Of course, here we have almost reached the PSD3 limit, but we also have some free space. So what happens in such situation usually is where the block is reorganized. So they, no, sorry, there is not enough space anyway for row 8. So they put it in another block. Then I delete row 1 is here. Update row 6. Okay, now that we update this row, maybe the block is reorganized. Not yet. So they put row 6 here. Update row 4. Okay, then they reorganize the block. The point is basically that they try to reorganize the block at the last possible moment. Okay, if it's not needed, they don't do it. Like deleting a row, as I said before, they just set a flag and they forget that it exists, and then they just put in the header, I have one deleted row, so that I know how much space I can save if I really delete it. But they try to not do work that maybe is not necessary at all. Now we update row 2. If there is not enough space here in the PSD3, basically what they do is they generate a migrated row. That's what we are talking about. So there is not enough free space in the block, and so to update it, they reduce row 2 to the minimum, and they put everything else in another block. Okay. Now let's see how it works in reality, since now we have seen what the concepts are. So I create one table. As you can see, it has an ID, which is a number, and 4 large strings. Okay. I insert one row, and notice that the size of the row right now it's small because I insert only 10 bytes of information for the 4 large strings. So I have a row which is smaller than, I would say, 50 bytes. Okay. Now if I check the row ID of this row, I can use the package dbms row ID to get information. So I see that it's in file number 6, block number 221, and this row number 0. It's the first row inserted in this block, and it always gets the row number 0. If we dump this block, okay, since I mentioned internal in the title, we have to look at some bits, otherwise it's not really interesting. The point is, when you dump a block, you get, okay, at the beginning just some information to identify the block, more, which is the RDBA is the address of the block, right? The file number and the block number. So it's 6 and 221, and we see that it's a data block. Where is the information? Yeah, data block. Okay. Anyway, if we skip the binary part, which is not readable, at least not for me. Don't know about you, but after the binary part, what we get is basically the header. For example, here we have the 2 ETL. Okay, in the interest and transaction list, we have the data header. Here I see that part of the screen is missing. Sorry. Okay. Okay. Let's start here. This is the table directory. We see that we have one table because it has only one row, and this is the row directory that tells us we have only one row inside this table. Okay, and here we see the table, the row itself. Notice that we have the 4 columns with 10 bytes each, plus the numeric value. And what is interesting here is the header. The header, basically, if you have the byte with the flex, we know whether the row is locked or not. Now it's locked from ETL number 1, and it contains 5 columns. There are the 3 information which are stored for every row. Now, what is interesting to point out here is that according to this flex, this row is the head, so the first means it's a piece which is referenced from our row ID, and it's the first and the last, so we do not have migration or chaining. Basically, all information are stored here. I am the head, I am the first and the last. That means everything is here. The other flags that you see or don't see in this case are used, for example, to specify that the row is deleted and stuff like that. Okay. So this is the initial, let's say, status. We have one row which is inserted and everything is in one block. Now, of course, the idea is to try to modify stuff to create a migrated row. What I do for that, I start inserting more data in the same block. How I do, I know that I insert data in the same block, basically because if the block has still some free space, Oracle from the same session will insert in exactly the same block as the first insert. If you are coming from another session, it depends on several, let's say, factors, but from the same session, 2 inserts will touch the same block if the block has enough free space. So I insert again a second row, and then I update all rows. And of course, the idea of updating this row is to generate some migrated rows, because the block after this insert here is almost full, and if I try to put 4,000 more bytes inside a block, there is not enough space. Okay, so if we check for example, here the position of the row with ID number 2, we see that it's in the same block, but it has a different row number because it's a different row. Okay, and if we check inside the dump right now, we can see that here we have the table directory. Of course, we still have only one table, but now the table contains 3 rows, and here we see the offset of the 3 rows. So the row with the number 0 is the first one that was inserted, the second one is this one, and the one with the number 2 is the one that I mentioned before. So if we check where this row is stored, we can take this offset, which is on others. We look inside the block, and here we see what kind of information is stored for this row. So what we see is that we do not have much information. The data is not here because end of blocks, just after the. So what we have is just the header, and the header that says, yeah, I am the head, so I'm referenced from a row ID. I am logged from somebody, and I have 0 columns. And in such a situation, since I'm not the first, last, and so on, basically Oracle adds here the row ID where the data is stored. So basically what we see here, this row ID will be this this pointer here. Okay, we have a minimal row piece with only 3 bytes for the flex, the lock, and the number of columns, and then the row ID that look at the data. Okay, so here we clearly have let's say a migrated row. Of course, with this row ID, what we can do is to check where to check the row piece, the second row piece, which is in the block. So if I copy it, I go back to here to convert row IDs and to extract information. You also have the package dbms utility. As you can see here, I can basically pass in some information and ask to give me the numerical value of this block. So in this case, you can see the row is still in file number 6, but it's in block number 223. So it's simply another block. So if we dump it and you go there and check what is stored, we have the typical header, so as always the flex, but notice here there is no H in the flex, so that means I'm not the first row piece. I'm the first and the last that contains data. I have 5 columns, which is the total in this case, but I missed the header. Okay, and basically here what you get in this case is where the header is. Okay, so you can see, and of course later on you have all the data. So again, to show you, for migrated row, the idea is that they reduce the header to the minimum, they put a row ID inside, and they put all the data somewhere else with a pointer from each side to know where this data is. Okay. Questions about migrated rows? It's okay. Now, if also we have seen how migrated rows are created and are stored. Now let's check the same stuff for row migration, for row chaining. Basically, you have row chaining in 2 situations. First, one row piece is not enough, also one row or one block doesn't have enough information to store a row. In the case I showed you before, since I have, for example, a row that can make 12 kilobytes, if I'm using 8 kilobytes block, of course I'm 16 kilobytes. Of course, I need at least 2 blocks to store the information, if not 3. Okay, depending on how much overhead I have in the headers. So if I have this kind of situation, I need more blocks, and it's where row chaining is used typically. Okay, so typically when you are using or seeing row chaining, that means that you have a row which is split in several pieces. Here I have 3 pieces, so the row starts somewhere, continues somewhere else, and ends in a third block. Okay, this is the first kind of chaining. The second one, which is called also intra-block row chaining, is caused by the limitation of 255 columns. Since you cannot have a row piece with more than so many columns, if you have a table with 500 columns, for example, you need 2 row pieces, and that's independent, how large the row pieces are. So what you can have is something like that. You have 3 row pieces, for example, you have 600 columns. Maybe these row pieces are really small, but that takes place in one block, but they have to be chained. Of course, this kind of chaining is, let's say, causing less trouble, because when you access a block, you have all information you need. It's just internal pointers inside the block. Okay, but these are the 2, let's say, cases of row chaining: rows that are too large, or that has too many columns. Okay. Important fact is that the split point can occur whenever inside the row. It's not that they split it, for example, at the limit between 2 columns, or not, you can split everywhere. Okay. And of course, a row can be migrated and chained at the same time. You can imagine that the migrated row we have seen before, so it was migrated in one block, and then you update again the migrated row that doesn't fit in one block, so they start chaining it. So we have a migration and then a chaining. Okay, and there is, let's say, no limitation here. Now if you go back to the demo and we look at a chained row, so now I insert a row from the beginning, a size of about 16 kilobytes. Of course, it doesn't have enough space in one block, but anyway, if we check where this row is stored, we get file number 6, block 227, row number 0. So we know that it's basically the first row in this block. Again, if we dump the information and we check what is stored inside the we can see that you have one table. This table contains a single row, and here is the position of this row. Of course, since it's the only one, it's just after the header. What is interesting here is to notice that the flex tells us that I am the row, the header piece. Okay, I am the first piece, but you see the L for last is missing. Okay, that means that it's a chained row. Okay. If you have migrated row, you must have first and last the flex in the same piece somewhere. If you have a chained row, it's not the case, because the first cannot be the last piece. Okay. So in this case, it tells us, okay, I'm locked from somebody. 2 columns are stored in this block. The first column is the ID, and the second column, you can see here I have 4,000 bytes of something. And the other 3 columns are stored somewhere else. Where they are stored, we have the row ID here. Okay. So if I take only the file number and the block number, I can note that the row is stored in this block. So if we dump it, what we see is one row This one is interesting because, as you can see, there is no flag which is set, so it's not the head, it's not the first, it's not the last. It's just a piece in between of something else. But of course, the important part is it tells you I have one column of information, 4,000 bytes, and it tells you where is the other piece. So if we take this pointer again, okay, I don't follow it, but if we follow, we will find the third, fourth, or whatever piece. Okay. So this is how the chained row are stored. Again, you have always the header and then the data which is spread across several tables. Now the PL-SQL block here is basically used to generate a table with 256 columns. The idea is to show you a case of intra-block chaining. Okay, so I create this table with 256 columns. I insert some data, and then I can dump the content. And basically, what you should find here is I have one table, 2 rows, even though I know I have only one row, but one row is for the first piece and one row for the second. And if I check here, I can see I see a row piece which is the last piece of the chain, contains 255 columns. And then if you go down 255, of course here I stored null to make it easier. What we see the second row, which is row number 1, which is the head and the first piece of this block. And if we check, let's say this row ID is pointing to exactly the same block. And you can see here is ED. If I go back, I should see here somewhere that this block is, yeah, the block number. So it's the same block. Okay, so we are chaining inside the same block, which again is not necessarily a huge problem since they're only internal pointers. But anyway, it's important to note that this kind of stuff exists. Also because when you start analyzing a table where you think you have migrated or chained row, it's important to know whether you have a problem with chained or migrated row, because the two have a completely different impact on your application, and to solve or eliminate them you have completely different approach. So if you do not know whether you are dealing with chaining or migration, yeah, it's not, I would say, easy or possible to solve the problem. And again, here the problem is that Oracle is not telling us whether we have a chained or a migrated row. Okay, every time they count the two, or they put the two in the same bucket, and we have no idea, just by looking at the statistics provided by Oracle, we have no idea in what kind of problem we have. So at the end, in my opinion, the only way to be really sure what you have is to dump a couple of blocks and to look inside and say, okay, here I have a chained row or I have a migrated row. But now let's see what kind of problem we can have with migrated and chained row. Let's start with migration. From a performance point of view, the impact depends on the kind of access path you have. Why it depends on the access path? Because remember, a migrated row is completely stored in one block. It doesn't contain part of the information here and part there. Okay? So if Oracle has to perform a full scan, okay, when he reads a block and defines a piece, which is the header, which contains no information, he can simply say, okay, I don't care, I threw it away, somewhere in the table, in another block I will find this row. Okay, so they continue reading the other blocks, and when they find a block with the second row piece, they will extract the information because all we need is in this block, and they can use it. So row migration for and full scan basically are no problem at all. That's just this overhead of 3 bytes plus 7, about 10 bytes in one blocks that you read. So it's really not important. From the other side, if you use an index range scan, and the index range scan reference with the row ID the head piece of the row, basically what you do, you get the row ID, you look at the block there, the block tells you the data is not stored here, you have to look at the data somewhere else. So if you have an index range scan, basically you double the index, the data access on the table for every migrated row. So if you have many migrated row, you will see many more logical, maybe also physical reads because of that. Okay. This is for migration. Chaining is different in the sense that since there is no block that contains all data, if you need all data, basically you always have to read every piece. Okay, and if you have to read every piece, of course you have to follow these pointers that we have seen before, and yeah, it's overhead. I would say the only exception is the case where you have, I don't know, 3 pieces, but the information you are looking for is only stored in the first 2, then Oracle will not access the third one to extract the information that is not required. But it's the only, let's say, exception. In general, we can say we have to access all the pieces. And when you access all the pieces, what is also very important to recognize is that even though maybe you are doing a full scan on a table, full scan, the idea is to get a big chunk of data from disk. But if during a full scan Oracle finds a head piece because of chaining, it cannot simply throw it away. What it has to do is to reconstruct the row, and so it has to do in the middle of a full scan single block access to get the information it's looking for. So when you have row chaining is where a lot of row chaining is where usually you see full scan which are performing poorly because they do a lot of single block access, even though the idea will be to do a few large IOs. Okay, that is because again they cannot throw away chunks, or they have to reconstruct a row every time they see one. Okay, so the overhead of chaining can be important. Okay, this is also the case where, for example, there is somebody, if you working with Exadata, HCC compression, where Oracle had quite a lot of problem, because basically in this kind of situation you try to take advantage of the storage cells to do the IOs, but at the end in this situation you end up that the database engines do single block access behind to get the information, and so you see the performance that are really bad for a smart scan. Okay. Then an overhead which is let's say the same in both cases, migration and chaining, is in case you have to lock one row. In fact, as we have seen, there is the byte containing the flex, and the lock byte is available in every piece. So when you lock a row, Oracle has to put a lock on in every block where this row is placed. So if you have the row over 4 blocks, he has to modify 4 blocks, take an ETL, add the pointer from the row to the ETL. So depending on how many migrated chained row you have, it might be an important overhead, because it's also generate undo and so on. Okay. So now, since we have seen we might have problem because of that, how we can identify and of course later on also solve this kind of problem. First of all, as I said before, Oracle do not provide a way to identify chained or migrated rows. Just mix the two concepts together. So when you check, for example, something like $cstat or mystat or sestat for table fetch continued rows. You get an increment. This statistic is incremented when you follow one of these pointers that we have seen before. Every time you follow one of those pointers, it increments of one this statistic. So here they are counted for both migrated and chained. So you know you have something, but you don't know what kind you are talking about. To use this kind of information, the idea could be something like that. Let's look at this one. I have a table. I insert 10 rows. Okay. You can see I have here I show only the ID and then the information about the row ID. So you can see that the rows were inserted in the same order that they were, let's say, generated. Okay. Now I update one row. As we have seen before, when you update a row, usually what it's happening that it changes position inside the block, or it can go in another block depending on the situation. Okay. Okay. Commit the change. Now, a way to know how many chained and migrated rows are available is to use the analyze table compute statistics statement. But again, even though this column is called chain count, it counts also the migrated rows. You have no way to know which kind you are looking at. So we know we have one chained row or one migrated row. Since we know the data itself, we can almost be sure that it's a migrated row because it 4,000 bytes. There is enough space in one block. But what is interesting in this case is to see that when I do a full scan, notice that now the row with the ID number 3, which is the row that I updated. Okay. You can see here as another position when you select it. And this is because it was moved inside the block. Okay. And of course the order of the data also changes. But by doing so, what I can check, and as I've seen before, with table fetch continued row, I can note that my session right now did 2 continued rows reads. Why 2 in this case? Sorry, it's because I didn't recreate the session. If I get a new session, here 40. Okay. Something strange happened here. I hope it's something which is related to the data dictionary. Because you have to think that every time you create drop tables, of course, you also modify plenty of other stuff. You also access the data dictionary, so you do not have control about that part of the code. Sorry, I started the wrong one now. Connect. Okay, so here is 0. Why 0? Because the row is still stored inside the same block, so I didn't have to look somewhere else. So something strange is happening here. Okay, this is, sorry, I forgot what the demo is doing. The idea is to show you what I was mentioning before. If you do a full scan, we do not get the fetch continued row. Then I create an index and I force the optimizer to use the index to access the data, and then we can see that the continued fetch is incremented. Sorry, I thought the demo was showing something else. Okay. So in any case, this statistic is a way to note that we have some row chaining or migration. But of course, you do not know how many are chained or migrated. Of course, you could compare this statistic with statistics like table fetch continued row, table scan row gotten or table fetch by row ID, and compare in average. I don't know if you access, for example, 10% of your row that you access are chained or migrated or not. So you can compare these three stats to know how many rows in average you access. Or as I said before, we can also use the analyze table statement. We have seen with the compute statistics, but also the list chained rows. Again, it lists also the migrated rows, not because it's called chained, it does only that for the chained rows. And then we can look inside this table. So with this method, we can see that we have some chaining somewhere. What I personally don't like about this method is that nowhere you have information about time. And what is important is to know how much time you lose because of that. And since there is no such statistic, you can just make some guesses and know, okay, if 10% of my physical reads are, for example, are generated because of row chaining, maybe if I go get rid of them, I might save 10% of the IOs, but it's really a guess because there is no information in the statistic provided by our code, and that's basically not good. Finally, a warning. We have seen before in the demo that I can use the analyze table compute statistics to put information in the chain count column in the data dictionary. Now what you must know is that the package dbms stats, it's not able to modify that information. So if you have scripts, I know people that have scripts, for example, that checks the chain count column to know whether they have chained or migrated row. Basically, if you use dbms stats to gather the stats, and it's basically what everyone is doing today, this column is not modified. Okay, just to give you an idea, I insert some data, 1000 rows, then I update the rows that I'm sure that I have many migrated rows. I gather the stats, and if I check the chain count, Oracle tells me I have no chained or migrated row. Okay, because again, dbms stats is not able to compute these stats. What is also interesting to point out is that if we have here a query that accesses this table, you can say that it takes an index range scan, cost 17. Fine. Now what is interesting to point out is that if we compute a statistic with analyze table compute statistics, you can see that the chain count is computed and stored in the data dictionary. Not only that, but also that the optimizer for the very same query than before used this information to increase the cost of the query, which is a sensible thing to do. But it's interesting to see that the optimizer is aware of this column, but dbms stats is not putting information into it. Okay. And what, in my opinion, is even worse, is that once you have executed the analyze table and you have something in this column, dbms stats will not overwrite it. So when you check user tab column or user table and you see last analyzed yesterday, and then you see chained count 500, you say, okay, I have 571 chained or migrated rows in my table. But in fact, it might be an information which is 10 years old or whatever. Because DBMS stats put some information into it, and when it puts something is 0, only when it's null. If it's as another value, it just keeps it. Okay. To check it, if I do a delete and then a gather, then I get the 0. But if I do only a gather, it keeps this information. So it's a bit, yeah, let's say strange how it works.
Aren't you potentially screwing stuff up though by doing the compute statistics? Because DBMS stats does some stuff that compute statistics doesn't. And so are you maybe having to do compute statistics and then instantly follow up by DBMS stats to make sure that your stats are consistent for the optimizer, but you do have that right value?
It's a problem. I do not advise to use the compute stats because you lose so many features, and
those stats are not used by the optimizer.
Which stats?
The stats gathered by analyze.
They are used, but they are different. So it's really not good to use them. And then using analyze, you lose many of the features implemented in DBMS stats, like the history locking, many features that we have. So I do not advise to use it, but
extended statistics, all that isn't covered in either, is it? So
yeah,
you would really, if you were doing this investigation, be on the safe side, run that, then run DBMS stats straight away, and then investigate.
Either run it straight away or back up the stats before and then do a restore. Because sometimes if you rerun, you get anyway a different different set. But I would say be careful with this chain count, because it's quite misleading what you can do with that. Okay. So now that we have seen that it's really not easy to identify a problem because caused by rows migration and row chaining, let's have a look to what we can do to avoid or solve a problem based on this kind of situation. First of all, as I already told you before, you have to understand whether you have chained or migrated or both. Because if you don't know it, you cannot solve the problem. If you have migrated rows, basically by setting PCT3 higher, it might be enough. You can fix it with a higher PCT3. Avoiding row chaining, of course, is much more difficult because if you need more space, you can only use larger block sizes. But sometimes also the larger block sizes are too small. If you have the limit because of 255 columns, maybe it's not a problem. If you have intra-block chaining, maybe it's a problem. But there you do not really have much choice than to reorganize, redesign the table, maybe put some stuff in a lob out of line or whatever. But it's not, you do not have a simple parameter you can set and solve your problem. Okay. Also be careful with PCT3 that if you set it, just setting PCT3, reorganize the table and thinking everything will be fine, it's usually not the case. Why? Simply because in a table usually you have rows which were already updated, so already have the maximum size, and rows that will be updated in the future. So if you set PCT3 now, the problem is that for the rows which are already at the maximum size, we'll end up with a lot of free space for nothing in the blocks. And for the rows that must be updated in the future, if you specify a PCT3 high enough, you should be fine. But then you lose a lot of space because of the owner. And also notice that the reorganization might also increase the size of a table, not only decrease it, depending on how you store your data. And to show you such a case, because I see people that say, yeah, alter table move cannot be cause any problem. Let's do it, but it can cause a problem. Just an example, I have a very simple table, couple of columns of 4,000 bytes. Insert 5 rows. Then I do an update just to check, yeah, I have a chained or chained or migrated row. I don't know from this information. The point is, let's say we have identified that we have some chained or migration, so we could say, okay, let's reorganize the table. I set the PCT3 to 80 because I noticed this migration, so I want to avoid that the row is moved. And then I do an alter table move. Now, what you must be aware of is that when you do an alter table move, the alter table move will use PCT3. Okay, and so here I have a table with 5 blocks and 1 chained or 1 migrated row. After the alter table move, I have 9 table blocks and again my chained row. So I didn't solve the problem. The table is almost doubled in size. Okay, just because in the way the move works, when they reformat the block, they say, okay, 80% free, so I have to keep this 80%. So when they find, in this case, a row which is larger than 20% on one block, they will generate chaining. So I remove migration and I add the chaining to my table. And I have plenty of free space everywhere. So be careful when you do this kind of reorganization. Sometimes something a bit more, let's say, complex is required. It's not just let's reorganize the table. Okay. So in general, alter table moves, be careful. If you have not so many rows which are migrated, a good way to solve it, I would say, is to create a temporary table, insert a select this table into the temporary table, delete them from the old table, and then reinsert them. When you do an insert of a migrated row, you are sure that you will get a non-migrated row. Whether you get a chained row depends on PCT3, as we have seen before. If the PCT3 is small enough, you get a row which is not migrated, not chained. If you have the PCT3 like in my previous demo 2i, then you get a chained row. So sometimes if you really you are really not able to solve the problem in another way, what we can do is to use the trick of minimize record per blocks, something that we don't like to do, but basically this one works in this way. As you have seen, setting PCT3 to I is a problem. So to reduce the number of rows that we put in one block, what we could do is just to have an idea what is the average row size when the rows have the maximum size. Okay. So if you know that the rows are 250 bytes, you can compute how many, or at least estimate how many rows you can put in one block. Okay. So let's say that you can put 20 rows inside in one block. So what you can do is create a table, insert 20 rows, execute alter table, minimize record per blocks, and from this moment on, you are sure that in this table, every block can have at most 20 rows. The PCT3, by the way, it's you can put it also to 0 because it's no longer relevant if you did your estimation correctly. And the good idea, the good part of this way of doing it is that when you insert a row and the row are small, they will leave a lot of free space inside the block because more than 20, for example, rows cannot fit in this block. But when when you insert rows which are large, it doesn't matter if there is enough space; they will be stored into it. So you can somehow keep a free space for the new rows, but store or pack the information for the old rows. But again, it's really a trick that you are willing to implement only if you have no other way to solve the problem. Because the fact is, again, if you have migrated and chained rows, it's not so easy, let's say, to solve. Okay, that was basically what I prepared for the second talk. I would say the most important messages are migrated are caused by updates. They can be avoided if you have a PS3 which is more or less correctly set, let's say, chained rows are caused by insert or update. Okay, I've just seen before, if the PS3 is too small, you do an insert, or if the row is really bigger than a block, you get a chained rows, but also update can generate them. Cannot always be avoided. Sometimes with larger block size you can do it, but not always. A row can be migrated and chained at the same time. Be careful, and there is no simple way to find out what the real impact is, because an information about time is missing. You know that you have some chained rows, some migrated rows, but again, from this information to guess how much time I spend because of that is really difficult, or almost impossible. So you have to try and see if you can really reduce the amount of work performed. Okay. Questions? Too late?